Let's solve this differential equation using power series method. We have x squared y double prime plus 3x squared plus 2xy prime minus 2y equals 0. First, we're going to show that x equals 0 is a regular singular point. To show that it's a singular point, we just divide by x squared. We get y double prime plus 3x squared plus 2x over x squared times y prime minus 2 over x squared times y equals 0, or y double prime plus 3 plus 2 over x y prime minus 2 over x squared y equals 0. Clearly, we have problems if x equals 0. So if x equals 0, both of these blow up, and so it is certainly a singular point. To show that it's a regular singular point, there's a couple of ways of doing it. Method number 1, let's take a look at the limit as x goes to 0. Let's take a look at this series. We have 3 plus 2 over x, and then multiply it by an extra x. So I've written it in this form where I have y double prime plus 3 plus 2 over x y prime, and we'll multiply it by an extra x. Then we get the limit as x goes to 0 of 3x plus 2, and that is equal to 2. So this has a limit. Next, we'll take a look at the limit as x goes to 0 of x squared times this bit, negative 2 over x squared. That's the limit as x goes to 0 of negative 2, and so that has a limit as well. So both of these limits exist, and so that shows that x equals 0 is a regular singular point. Okay, so that shows that x equals 0 is a regular singular point. Part 2, find the two roots of the indicial equation. Again, there's a couple of ways of doing this. The fastest way is to write directly r times r minus 1. Then I have this 2, so plus 2r, then minus 2 equals 0, and solve for r. So I get r squared minus r plus 2r minus 2 equals 0. That gives r squared plus r minus 2 equals 0. So that this factors as r minus 1 times r plus 2 equals 0. So I have two roots, r equals negative 2 and r is equal to 1. There's another way that this can be solved. We'll do this later when we get to the series expansions. But that's the two roots. Now we'll notice that these are separated by an integer, so something funny might happen when we start solving for the power series solution. And it turns out it doesn't happen in this particular example. But that doesn't always happen. Okay, so there's the two roots of the indicial equation. Let's jump to part 5. Based on the differential equation, what is the minimum radius of convergence for the power series? Now, we've already written this with x squared in front, so that's x squared y double prime. Let me factor an x out of this. So x times 3x plus 2 times y prime. Then I have plus negative 2 times y equals 0. The things in parentheses do not blow up. So that this part in parentheses does not blow up, this part in parentheses does not blow up, and so we're guaranteed that the minimum radius convergence is infinity, that this will converge for all values of x. Parenthetically, if we let x equals 0 here, 3x plus 2, then I get the same 2 that I saw here. So if x equals 0 in this first parentheses, I get the same 2 that I saw here. Also, it's not a coincidence that the negative 2 that I see here is the same negative 2 that I see here. So that is an alternate way of being able to figure out these two things for setting up the indicial equation. Okay, so let's see. We've done part 1. We've done part 2. We've also done part 5 to find the minimum radius of convergence. Okay. Find the recurrence relationship for the coefficients. So this is going to take some work. So let's get a fresh piece of paper for this one. So we have that, just copy the problem over again, that x squared y double prime plus 3x squared plus 2x times y prime minus 2y equals 0. And we're going to set up our solution as y is equal to summation n equals 0 to infinity a sub n times x to the n plus r, where we just got done saying that r will be either equal to 1 or equal to negative 2. Okay, y prime will be equal to summation n equals 0 to infinity of n plus r a sub n x to the n plus r minus 1. Now if I multiply that by 2x, I get summation n equals 0 to infinity of 2 n plus r a sub n x to the n plus r. And I add an extra x in the exponent because of this x to the first out here. All right, so no shifting necessary because I have x to the n plus r. Next, we have the 3x squared part to worry about. 3x squared y prime is equal to summation n equals 0 to infinity of 3 times n plus r a sub n x to the n plus r plus 1. Okay, now I have to shift the index, so this is going to take me to n equals negative 1 to infinity of 3 times n plus r. Sorry, I got it backwards. N equals plus 1. N equals 1 n plus r plus 1. Okay, that's minus 1 here. Then x to the n plus r. Okay, let's double check to make sure this works. If n equals 0, I have 3r here. If n equals 1, I have 3r here as well, because at 1 minus 1 is 0. If n equals 0, I have r plus 1. If n equals 1, I have r plus 1. So everything checks. Okay, next we have y double prime. So y double prime is equal to summation n equals 0 to infinity. So I come back to this line and take a second derivative, n plus r times n plus r minus 1 a sub n x to the n plus r minus 2. Then if that gets multiplied by x squared, n equals 0 to infinity, n plus r minus 1 a sub n x to the n plus r. Okay, so putting it all together, we have x squared y double prime plus 3x squared y prime plus 2x y prime minus 2y. That's going to be equal to, all right, so here I have a 0 term, here I have a 0 term, here my lowest term is 1. There I've got a 0 term, and on the y I've got a 0 term. So let's take the 0 terms first. If n equals 0, on this part I have r times r minus 1, a sub 0 x to the r. Then on 3x squared y, I don't have a 0 term, so I'm not going to worry about that. 2xy prime, I have a 0 term, so plus 2r a sub 0 x to the r, setting n equal to 0. And then finally, minus 2y. The 0 term here will be minus 2 a sub 0 x to the r. Okay, then I have plus summation n equals 1 to infinity of n plus r minus 1 a sub n x to the n plus r. I'll put that in last. Then I have plus 3. I forgot the a sub n minus 1 here, I apologize. Plus 3 n plus r minus 1 a sub n minus 1 times x to the n plus r. Then the next bit I have plus 2 n plus r times a sub n. And then lastly, minus 2 a sub n. And each of those gets multiplied by x to the n plus r. Okay, and so that is the expansion, and this is supposed to be equal to 0. Now if I set this equal to 0, that means I have r times r minus 1 plus 2r minus 2 equals 0. And that will lead to r is equal to 1, r equals negative 2 as before. So that tells me the values of r that I have to use. Okay, then we also have to have that the thing in brackets is 0. So that means that n plus r times n plus r minus 1 times, and I also have this part here, plus 2 n plus r times a sub n, plus, then I've got a bunch of things times a sub n minus, and I forgot the minus 2 here, I apologize, minus 2. Okay, then I have times the a sub n minus 1. I've got this last bit. I've got 3 n plus r minus 1, a sub n minus 1 equals 0. Okay, I can simplify a little bit. So on these first two terms, I can factor the n plus r out, and then that gives me n plus r minus 1 plus 2 for n plus r plus 1 minus 2 a sub n. That will be equal to negative 3 n plus r minus 1 a sub n minus 1. And so that leaves me with a sub n is equal to negative 3 n plus r minus 1 a sub n minus 1 over n plus r times n plus r plus 1 minus 2. And so that will be our recurrence relationship. And in this problem, unlike most of the others in this series, there's no reindexing necessary. It happened to fall out that I get a sub n equals something involving a sub n minus 1 when I come out the other end. Okay, we got two cases to worry about. First, let's deal with the case that r is equal to negative 2. If r equals negative 2, then this becomes a sub n is equal to negative 3. Then n minus 2 minus 1 becomes n minus 3 a sub n minus 1 divided by n minus 2 times n minus 1 minus 2. Okay, so let's see what happens. We start with a sub 0. A sub 1 is going to be equal to negative 3 times negative 2 a sub 0 divided by, if I plug in 1, I get negative 1 times 0 minus 2. So that works out to be negative 3 a sub 0. A sub 2, so plugging in 2, we get negative 3 times negative 1 times a sub 1 over, plugging in 2, we get 0 times 1 times negative 2. So the practical upshot is that I get negative 3 halves a sub 1, which becomes 9 halves a sub 0. But look what happens at n equals 3. If n equals 3, I get negative 3 times 0 times a sub 2 over 1 times 2 minus 2. I'm multiplying by 0 here, and so that's equal to 0. If I keep going, a sub 4 is going to be equal to negative 3 times 1 times a sub 3 over 2 times 3 minus 2. A sub 3 is 0, and so I get 0 again. And so it turns out that a sub n is equal to 0 as long as n is greater than or equal to 3. So this solution is actually quite easy. We get y of x is equal to a sub 0 times x to the 0 minus 2 plus a sub 1 x to the 1 minus 2 plus a sub 2 times x to the 2 minus 2. And then all the other terms are 0. And I have the minus 2 here corresponding to r equals negative 2. So the practical upshot is I get a sub 0 times x to the negative 2 minus 3 x to the minus 1 plus 9 halves, and that is my first solution. I get this thing looks like this. And I could rewrite this as a sub 0 as 9x squared minus 3x plus 1 all over x squared. And so that is the first solution I get. And so this infinite series, quote-unquote infinite series, actually truncates and only has 3 non-trivial terms. Okay, that's our first solution. Our second solution, let's come back to this. And this time we're going to let r equal 1. If r is equal to 1, we get a sub n is equal to negative 3n a sub n minus 1, because 1 minus 1 is 0, over. If r equals 1, I get n plus 1 on the bottom. And then if r equals 1, I get n plus 2 here, minus 2. Okay, let's see if I can do better than this. I get negative 3n a sub n minus 1 over n squared plus 3n plus 2 minus 2. So negative 3n a sub n minus 1. 2's canceled. That leaves me with n times n plus 3 on the bottom. Then I can cancel the n's, and I get negative 3 a sub n minus 1 over n plus 3. And so that is the recurrence relationship for this infinite series. Okay, now let's see if we can figure out a pattern for the closed form solution. So a sub 1 is going to be equal to negative 3 a sub 0 divided by 4. A sub 2 is going to be negative 3 a sub 1 divided by 5. And so that works out to be 3 squared over 4 times 5 times a sub 0. A sub 3 will be equal to negative 3a sub 2 over 6. So that's 3 cubed over 4 times 5 times 6 times a sub 0. And interesting. So let's see. I can write this as, this first one is equal to negative 3 times 6 a sub 0 over 4 times 3 times 2 times 1. If I multiply this one top and bottom by 6, I get 1 times 2 times 3 times 4 times 5, a sub 0. On this one, if I multiply top and bottom by 6, and I forgot the minus here, multiply by 6, a sub 0, then I get 1 times 2 times 3 times 4 times 5 times 6. And so it looks like that a sub n is going to be equal to negative 1 to the n times 3 to the n times 6 divided by n plus 3 factorial. Also, if I let n equals 0, this would be a sub, and I forgot the a sub 0 here. If n equals 0, I get negative 1 to the 0 times 3 to the 0 times 6 over 3 factorial a to the 0, which equals a to the 0, a sub 0. So that actually checks. So the pattern actually works for all values of n. The base case actually happens to work for this example. So y of x is equal to summation n equals 0 to infinity of a sub n times x to the n plus 1. In this case, a sub n always works out to be this. So negative 1 to the n times 3 to the n times 6 times a sub 0 over n plus 3 factorial x to the n plus 1. Okay, now this actually simplifies using Taylor series. To see why this simplifies, let's write this as summation n equals 3 to infinity. So I'm going to shift by 3. Negative 1 to the n minus 3 times 3 to the n minus 3 times 6 times a sub 0 Then I have over n factorial, and here I have x to the n minus 2. So let's rewrite this as summation n equals 3 to infinity. Okay, I have a negative 1 to the n. I have a 3 to the n. I have an x to the n over n factorial. Okay, what's left? I need a 6 out here. 3 to the minus 3 is over 27. There's a minus sign here because negative 1 to the negative 3 is negative 1. And also the a sub 0. Okay, now you should recognize this to look like this. So this is negative 6 a sub 0 over 27. This is summation n equals 0 to infinity of negative 3x to the n over n factorial. Now I'm starting on 0 now as opposed to 3, so I've got to subtract off a couple of things. Minus 1 plus 3x minus 9x squared over 2. And then finally, the sum that I see here is actually the power series, the Taylor series expansion, for e to the minus 3x. Minus 1 plus 3x, and I forgot the x, one other thing I forgot, I apologize. X to the minus 2 here, so I need an x squared down here. X squared down here, x squared down here. So negative 1 plus 3x minus 9x squared over 2. Okay, so the practical upshot is that instead of this time I don't have infinite, I have the infinite series actually is something that is recognizable from our previous studies of Taylor series. And so we get that y of x is equal to, this is a constant. Then if I divide by x squared, I get negative 1 over x squared plus 3 over x minus 9 halves plus e to the minus 3x over x squared, where I've taken the 6a naught over c2 and just called that a constant c. And so this also is a second solution of the differential equation. And so that is the second solution of the differential equation. Okay, so let's take a look at how we've done in here. So we found the recurrence relation for the coefficients. We found a closed form for the coefficients. And in fact, we showed that the one series only has 3 non-zero terms, while the other series can be simplified considerably by using a commonly known Taylor series. And so there is one answer. And the other answer, which we found earlier, if I can find my notes, was this part right here, constant times 9x squared minus 3x plus 1 over x squared. So those were the two answers. The one part that I did not do in this video, which we've done multiple times in other videos, is describe how a computer program can be used to compute the coefficients of the two linearly independent solutions. This one is I'll do that for the non-trivial series. So for this one, we have A, B, 1, 2, 3, 4, 5, 6. So this will be equal to 0, and then I filled down the pattern. The first term is whatever it is. And then the next term will be equal to negative 3 times the previous term divided by n plus 3. Then if I fill that down, then Excel can give me the coefficients.